Hello student, today we will continue topic surface energy. As we already discussed about the surface tension, we know that due to surface tension, liquid has a tendency to occupy minimum surface area. If the area of liquid has to be increased, we have to do work against the force of surface tension, because surface tension minimizes the surface area, and if we want to increase the surface area, we have to do work. Right? This work done is stored in the liquid surface film as its potential energy. You might pierce the soap bubble, it breaks into various small droplets and move away because of that potential energy. The potential energy per unit area. The potential energy per unit area of the surface film is called surface energy, or we may define the surface energy as the amount of work done to increase the area of the surface film through a unity is called surface energy. Now let us say we have a U-shaped wire. This U-shaped wire is A, B, C, D. A, B, C, D. And this wire is taken as horizontal wire. And in this wire, the liquid is filled. The liquid is filled in this wire, and the length of a small rod PQ is L. The length of the rod is PQ, and it is, if we consider here a film in which the liquid is filled like this one, the surface tension T will applied on the two surfaces of the film. Here is the film. The film has two surfaces. This is film. The one surface is topmost, the other surface is down way. The upper surface and the lower surface. So if we consider the length L, this length L will be comes in two times. The L of the upper surface as well as L of the lower surface of the film. As we know, the surface tension T is equal to force acting per unit length. So this length L comes twice here. The length L of the upper surface and length of the lower surface of the film. Hence the force F will be T into 2L. Now to keep the position of this wire PQ to its original position, that is P dash Q dash, as it is shifted by distance x by the surface tension, and we want to take this wire PQ again come back to P dash Q dash, so we have to apply a force in opposite direction so that PQ comes again at its original position P dash Q dash. So we have to do some work. The work done is equal to force into distance. The work done is equal to force into distance. We already calculated the force. The force is 2 into T into L. Force is equal to T into 2L. And the distance is x. So it is T into 2L into x. What is L into x? The L is length and x is the distance travelled by the wire PQ. So L into x is the area. So this is the change of area. That is L into x for upper surface and L into x for lower surface. It means the change in area will be 2L into x. So we may say the work done to carry this PQ wire again its original position, the work done will be the surface tension into change in area, that is T into ds, or you may simply write it T into delta S or T into delta A. Delta S is change in area. You may write also T into delta A. This change in area, this work done is stored in the surface of film as potential energy. So increase in the surface energy is surface tension and change in area. When a large drop is broken into a large number of small droplets, if we have a large drop and it broken into very small droplets, and the number will be quite large. These are droplets. There is an increase in surface area. It means the drop has lesser area than the droplets. It means there is a change in area. Hence, work has to be done. How much work done? The work done will be the surface tension into change in area. We will discuss this equation in solving a numerical also. Now let us solve some numerical based on surface tension and surface energy. Here is a question. A soft film is formed on a rectangular frame of length 0.5 meter. 0.05 meter. Here is a frame. Here is the frame and it is dipped inside a soap solution, and the length of this frame is L. What is given here? The length of the frame is L and it is 0.05 meter. This is dipped inside a soap solution. This is soap solution. The frame hangs from the aim of a balance. This frame is hanged from the aim. To balance this one, we have to use an extra mass, and this extra mass to balance this frame comes as 3 into 10 to the power minus 4 kilogram. And here is the film inside the frame. We have to find out the surface tension of the soap solution. Surface tension T we have to find out. Now what is given? The length of the frame, mass to balance this frame, and T is surface tension. So first we have to find the force on the left wing because of the surface tension. We know force is upon length is the surface tension. As there is a film and film has two sides, so the effective length L will be 2 into L because this film has two surfaces, upside and downside. So it is 2 into 0.05 meter. This is effective length. That is 0.10 meter. Hence the surface tension is equal to force upon effective length, that is 0.10. The force is the weight, that is m into g. The additional mass which balances the film is m, and the weight, which additional weight is required, is m into g, and it is 3 into 10 to the power minus 4 into 9.8 upon 0.10. So it will come, we may remove the decimal, 3 into 98 divided by 1 into 10 to the power minus 4, or it is equal to 3 into 8, 24, 2, 27 and 2, 29 into 10 to the power minus 4. It is equal to 0.0294. The unit of surface tension is Newton per meter. So this is the surface tension of the soap solution, and we may write here it is the answer. Now let us take another example, another numerical. In next numerical, we have to calculate the energy required to split a drop of water of radius 2 into 10 to the power minus 3 meter into 1000 million droplets of the same size, given that droplets are of same size. The surface tension of water is given as 0.072 Newton per meter. What is going on here? Here is an atomizer in this figure. An atomizer, by the pressure difference, take a drop on the nozzle, and this drop is sprayed into very small droplets by this atomizer. So here is the drop, and here are the droplets. Now what is happening here? The drop is sprayed into droplets, so we have to give some energy to make the droplets, and then we have to calculate that energy. The energy may be given by the rubber balloon here, or maybe piston attached with the atomizer. So first of all, to find out the solution, we have to write the given things. What is given here? The radius of drop, that it is capital R, and it is 2 into 10 to the power minus 3 meter. The number of droplets, the number of droplets the number of droplets is 1000 million. 1000 million. Millions means 10 to the power 6. So the number of droplets comes out 10 to the power 9. And the surface tension of water, the surface tension of water it is represented by T or by sigma. Sometime in some book you may say the surface tension is represented by sigma as well, and it is 0.072 Newton per meter. So when a drop of radius r is broken into droplets, the volume of the drop will be equal to the volume of droplets. So volume of the drop is 4 by 3 pi r cube, as it is spherical, and the volume of the droplets will be n is the number of droplets into 4 by 3 pi small r cube. If each droplet has radius small r, r is radius of droplet. So 4 by 3 pi, 4 by 3 pi will cancel each side. We will have capital R cube is equal to n into small r cube. The value of r is given as 2 into 10 to the power minus 3. 2 into 10 to the power minus 3 whole cube is equal to n, the number of droplets, that is 10 to the power 9, the small r cube. So we are able to find out the radius of droplets by this equation. So r cube is equal to 8 into 10 to the power minus 9 upon 10 to the power 9. It means it is 8 into 10 to the power minus 18. So small r is equal to, we may find the cube root both sides. The cube root of 8 is 2 into 10 to the power minus 6. 1 by 3 of 18 is minus 6. So this is the radius of droplet. Now we have to find the energy required. And we know the energy required, W is equal to surface tension into change in area. We already find this equation as. So what is the change in area? That is the area change due to droplets in drop. So first we have to find out delta S, change in area. So change in area is equal to area of droplets minus area of drop. So delta S is equal to area of droplet. There are n droplets, and area of each spherical drop is 4 pi small r square minus area of drop. It is also spherical, so it is 4 pi capital R square, right? Then delta S is equal to 4 pi taken out n r square minus r square, capital R square. Or delta S is equal to 4 pi, n is 10 to the power 9, 10 to the power 9 droplets are there. R we already find out, 2 into 10 to the power minus 6 meter. Square minus capital R is 2 into 10 to the power minus 3 meter square. So change in area is 4 pi two into 10 to the power 9 minus 12, that is minus 3, minus, 2 square is 4, minus 4 into 10 to the power minus 6. Now we may take the value of 4 outside. So 4 4s are 60 pi 10 to the power minus 3 is also taken out. So it is 1 minus 10 to the power minus 3. Hence, the change in area is equal to 16 into 3.14 into 10 to the power minus 3 into 1 minus 10 to the power minus 3. 10 to the power minus 3 is 0.001. So it comes out 0.999. Nearly 1. So delta S comes out 16 into 3.14 into 10 to the power minus 3 meter square. Right? So we may calculate it. It is 16 into 3.14. It comes out 50 into 50.24 into 10 to the power minus 3, which is approximately comes out 0.050 meter square. You may write also 24. So 0.0524 meter square. Now we have to find out the energy. So W will comes out T into delta S. T is 0.072 into 0.05. Right? So we may calculate it again. 0.72 into 0.05. It comes out 0.0036, that is 3.6 into 10 to the power minus 3 joule. So by this method we are able to calculate the energy required to split the drop. Hope you are familiar with surface tension, surface energy, and how to solve the numericals.